Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Vishal Gajjar with us today. Hey, Vishal.
Hey, Frank. Thanks for having me.
Oh, well, thank you so much for being willing to talk about your really lovely article. I think it's a great one. So where are you located at?
So I'm currently at UC Berkeley in the astronomy department. I'm an academic researcher in the department, and I work on various different topics, including the one that we are currently going to talk about.
Very good, very good. And what is summer like today on August 6th at roughly 2 p.m. in the Bay Area?
To be frank, Bay Area is probably very good in terms of summer and winter, both seasons. It's not too hot, not too cold in either way. But definitely if you go inland, it's pretty hot.
Yeah, speaking of those inland people, so I'm pretty far inland, so I'm in Phoenix, an ex-ocean, and yeah, we're good and toasty today. We're probably up around 40 C or something like that today.
Yeah. Oh my God, that's pretty hot.
So where are you at? Are you at Berkeley? Are you on campus?
Yeah, I'm on campus. So campus started we are kind of getting back to the office schedule as much as we can. But recent this Delta variant, we are currently still having a mask mandate if we are more than one person in a room. So, which is, I think, a good thing that is probably going to be useful. But
it looks very pipes and wires and lights and all kinds of Brazil kind of like stuff.
Yeah, that's the astronomy department's architecture is kind of like that. Like they didn't like to have a false ceiling. They left all the wires and the pipes hanging. It kind of gave us all aesthetic feels.
Yeah, it gives it a very industrial kind of look, right? This is like industrial astronomy. It's fantastic.
Yeah. I mean, if you are around in the Bay Area, just drop me a mail and I'd love to show you our lab. We have a pretty nice breakthrough listen lab that we'd love to show you.
I will take you up on that offer, probably maybe this fall or winter, particularly when we see where the Delta goes. But yeah, thank you very much for that. Vishal, what do you like to do for research?
So I do various things. My main background is in pulsar. So neutrons, like fast rotating neutron stars, is where I kind of grew up and did my preliminary research on. But moving to Berkeley, my focus changed on looking for intelligent life, because that is something that I'm kind of always was fascinated with. And Berkeley had that opportunity for me to kind of explore that research area. Cool. So I'm part of this team called Breakthrough Listen, where we are actually conducting one of the most comprehensive search for evidence of intelligent life. And this paper that we recently published is one big component of the Breakthrough Listen campaign to search for evidence of life in the universe.
Cool. And that is going to bring us to this very lovely article. The Breakthrough Listen Search for Intelligent Life near the Galactic Center. And Vishal, take us away.
Yeah, thanks, Frank. So we are quite excited about announcing our first series of these paper on searching for intelligent life in the Galactic Center. So what we thought is that it is useful to kind of give an overview of what exactly we want to do with the survey, and showcase some of our preliminary results, just to outline what exactly we are planning to do. To give you a little bit of background on Breakthrough, so Breakthrough is a 10-year long project. We are in 5th year right now. It's a $100 million project to search for evidence of intelligent life across multiple set of targets. Like one of the target is a galactic center. We also have other targets like nearby stars. We also are looking for nearby galaxies. So Galactic Center is one component of that. But what is special about Galactic Center campaign is that we want to survey it entire across the electromagnetic spectrum, especially in the radio window. So looking at from the ground-based instrument, from radio telescope, you could actually go from like all the way to like low frequency as low as like 50 megahertz to all the way as high as like several hundred gigahertz. What we want to do is to do 1 to 100 gigahertz of survey, because that's the very cleanest part of the band. If you go to lower than 1 gigahertz, typical background in the galaxy kind of dominates. So it's pretty hard to look for things below 1 gigahertz, especially Galactic Center, where you have a lot of synchrotron emission. A lot of continuum emission will increase our system temperature quite a lot. So it's not really fruitful to do survey below 1 gigahertz. Obviously, we have planned to do it, but the sensitivity will be limited. But 1 to 100 gigahertz is relatively cleaner. Above 100 gigahertz, obviously, the atmosphere, the water molecules in the atmosphere start creating issue, and then you are limited by the sensitivity. Also, the weather condition needs to be very perfect in order for us to conduct these observations.
Yes.
So 1 to 100 gigahertz is an ideal range. So what we want to do is to survey the galactic center for 600 hours, combined with 2 radio telescopes. One is the Green Bank telescope, which is in the US, and second is the Parkes telescope, which is in Australia, to survey starting from 1 to 100 gigahertz. I mean, the exact frequency is 0.07 to 93 gigahertz, but that's essentially what we have planned to cover.
Yeah. Okay.
So why, first of all, like if one asks this question, why are we so interested in Galactic Center? Like what is so special about Galactic Center? So the reason why we are interested in Galactic Center is that the Galactic Center is one of the most highly energetic region in our galaxy. It has a lot of interesting astrophysical phenomena. Along with that, it has the largest concentration of stars in that line of sight. So if you look at in any other direction in the sky, looking towards the galactic center will give you the largest number of count of stars. We know that we don't know what kind of life might be out there. We know that Earth was very unique in some regard, but it's not necessary that life would arise on similar planet like Earth. It could be on other planets rotating around, maybe like a giant star. So we have expanded our region of sort of parameter space to look at all classes of stars. So you just simply look at, you definitely need a star and a planet, at least as for now, what we are currently thinking about. You may have like a floating life. That's like, how do you find them? That's a different thing. But like if it's actually on a planet or around a star, then you kind of try and maximize research where you can encounter larger number of these stars. And Galactic Center is one direction where you want to where you have the largest number of these stars. So if you look at the figure number 1, I scroll down, what we did was that we did like a rough estimate. Obviously, there are a lot of assumptions that is taken, but assuming the star formation that we have in our galaxy, if you calculate how many habitable planets might be, if you go closer and closer to the galactic center, it kind of goes up. So we are somewhere around 8.5 kiloparsec at distance, where 1 in every 100 star is likely to have habitable planet. But if you go closer and closer, 1 in every 10 star is likely to have habitable planet. So that's phenomenal. So there are 2 things that's happening there. 1, the number of stars are higher. Second, the number of habitable planets that you will find is also higher. So if you kind of simply take the probability that what is the chance for life to develop, and you kind of apply this across the galaxy, the galactic center comes out to be an ideal region where some life might have already developed, because these planets, there are more number of chances that can happen in that region compared to anywhere in the galaxy. Sorry, I think I missed you. Were you saying something?
No, I'm good. Okay. I'm with you.
So we kind of roughly calculated the number of sort of habitable planets in the line of sight. So what you're seeing in this figure, the x-axis is the radial distance from galactic center to all the way to like 15 kiloparsec. And the y-axis is the fraction of star with a habitable planet, assuming what the model that we have. So if you read our paper, we have actually given explanation for like why we think the habitable planets are more likely to form closer to the galactic center compared to other parts of the galaxy. But that's our main motivation. Like if you have so many such interesting systems closer to the galactic center, that would be an ideal place to look. That's reason number 1. We also think there are other reasons. For example, reason number 2 is that, let's say there is an intelligent life in the universe and they want to place a powerful transmitter somewhere which is visible to across entire galaxy. There is this very classical problem in the field of SETI, like which direction to look, which is the ideal place to look for intelligent life. Is there any particular stars are ideal? Is there any particular direction which is more favorable to and likely to give more promising results? The galactic center always kind of leads and always is kind of beats everything. Because if you place a transmitter at the galactic center, it is kind of going to broadcast throughout the galaxy. Everybody in the galaxy would know about the existence of the center, and they will one time or the other in their entire history of astronomy, they will look at the galactic center. So it's very likely place to put a transmitter. It's very likely place to be discovered. So if you want yourself to be discovered, you put it somewhere that is very easy, accessible for everybody. This is kind of like what we call the shelling problem, right? If you are in a game theory, like if you have multiple parties and they want to kind of reach to a similar conclusion, so then you have to kind of envision that what would the most logical step the other party might take. For example, like if you want to meet a stranger in the New York City, what time and place you might choose to kind of meet. And you can say that at midday in Grand Central, maybe, yeah, that's an example. But yeah, so this is what we call in a game theory, this is what called the shelling point. So in terms of for SETI as well, galactic center is an ideal shelling point. So if ET are smart enough, then they might put a powerful transmitter at the center.
Okay.
So that's the reason number two. Reason number three is that there are other civilizations that have, because stars are much closer in that region. So any civilization which develop in that area will become technologically advanced pretty fast, because let's say you have a star which is quite close to you, you will become spacefaring civilization pretty quickly. It will kind of motivate you naturally to travel to other stars because it's much closer to you compared to like 4 light years we have right now.
Right. Right.
So people have done modeling. So if there is a civilization, if you have more dense cluster, the population will expand pretty fast. So you'll become more highly technologically advanced pretty quickly.
Okay.
And fourth reason is the ancillary science that we get. And that's like, as I mentioned earlier, Galactic Center is as a trove of sort of like a trove of other interesting astronomical objects out there. One of the classical problem, like my background is in pulsar, one of the things we are in the pulsar field, people are always fascinated and are searching for, is the pulsar black hole binary. A pulsar rotating in around a black hole. We know it's kind of very hard to find, but fortunately for us, we know there is a black hole. So if you find a pulsar which is rotating around the central massive black hole of our galaxy, that actually helps us solve a lot of issues that we have. I mean, that it may have us solve some of the Einstein's general theory of relativity, for example, these things called no-hair theorem about black hole, whether black holes are spin, and all of these things will be able to kind of assess if you find a pulsar around the black hole. So our data that we are going to collect has all of these other applications. So this is not just going to be useful to look for intelligent life, but we are actually already made all of our data public. So anybody who is interested in looking for pulsars, they could do that.
Yes.
All right. So if you scroll down, and I can talk about a little bit about our survey outline, what exactly we are planning to do.
There you go. There's your shelling point.
Yep.
SGRJ 45.
Right.
RB.
And as I said, there are other ancillary science. So this is the way we are going to tile the region. So is what I'm showing you here. So this is the galactic latitude and galactic longitude in X and Y axis. The individual red circle you see, that's the size of our radio beam. So radio telescope, as most of you know, cannot look at the large part of the sky. It only looks at a very small piece of sky. It's actually bigger than the optical telescope, but it's still small. It's small, right? So yeah, it's relatively small. It's not like as you are looking through with your eyes. So it only looks at a very small part of the sky. So in order to cover like this 2 degree by 2 degree, 2 degree by 1 degree patch of area around the galactic center, we have divided into multiple small segments. Okay. So each individual red circle you see is actually a one beam. So we need to have something around several hundred of these beams filling out the entire region in order to kind of cover it. So if you scroll back, I can talk about a little bit about the table, and that gives you an idea about how much time that we are planning to spend. Scroll down. Yeah.
There we go.
So this is the table that kind of gives you an idea about various different frequencies. So as mentioned earlier, we plan to do from 0.7 gigahertz, like 1 gigahertz, to all the way to like 93 gigahertz. Right. So table one shows you different receivers that going to be used for this application, and what are these different frequency ranges these individual receivers are going to be sort of focused on. And as you can see, we more or less cover the entire frequency range. There are obviously few maybe gaps here and there, like between there are some frequency ranges which may not ideally be covered, but we more or less cover the entire electromagnetics, entire radio spectrum. Yeah. You can read the number of sort of pointings that we need in this that how many number of sort of individual pointings that we would need, because as you go in higher and higher frequency, your beam becomes smaller and smaller. Oh, yeah. So as you go high frequency, your number of beams that you need in order to kind of cover the entire region the number gets larger and larger. So if you look at table number 2, we try to give that sense of how that increases. Obviously, we can't cover the same region of the sky as at all frequencies, because that will run into this issue of actually having thousands of beams. So the survey region is going to change slightly as you go from lower to higher frequency. So at the lowest frequency, obviously, we can cover a little bit of large part of the sky, which is 2 degree by 4 degree. But at the highest end, we can only cover 1 arc minute by 1 arc minute. Right. And even that 1 arc minute, we're still going to have 144 beams. So in order to fill this 1 arc minute region, you need to have 144 beams to really cover them with equal sensitivity. So that's basically gives you an idea about what exactly we are planning to do. So if you scroll again down, we can show you some of the way we are doing the pointing. You can skip this. We can go to figure number 4, which is like a general figure for all of the bands. Yeah. So this is, I kind of already explained this to you. Like if you go to high frequencies, your beam gets smaller. And in order to kind of cover it, we actually, this is how the region, and this is how the beam placement is going to be. Now, there is a issue, or there is a thing that we need to tackle when you're looking for signs of intelligent life. So in the field of SETI, when you try to look for signs of intelligent life, we typically find signs of our own technology, because we are intelligent. We produce a lot of radio emission by using mobile phones and Wi-Fi's and and your cars produce a lot of radio waves. So everything that we use for our technology produce a lot of radio waves. And they all interfere with our search. So what we need to do is that the way we do it is that we look at multiple parts of the sky. We hope that that signal is coming from only one part of the sky, not from multiple parts of the sky. Because it's unlikely that there are multiple ETs doing exactly same thing. So if we detect a signal in only one part of the sky and not in the other, that way you can discriminate what's local and what's actually coming from what's basically coming from sky. Yes. So by doing this beaming, it also helps us. So what we plan to do, and we have already demonstrated it, is that we look at one part of the beam, we look at in one beam, we look at the data and we look for this interesting signal, and then we look at the nearby beam. If the same signal repeats in the other beam, that's obviously due to some kind of interference, because interference generally comes no matter where you look. So they have some directionalities, but typically for that very small separation in the sky, you don't see a lot of difference in their signal strength. They still come with similar strength if you look like few degrees away within each other. So we use that to our advantage in order to discriminate what's terrestrial and what's skybound. So this multiple beaming actually help us in that regard. So let's scroll again down, and I'll show you some of our very preliminary results from, so what we did exactly. So these are some of the dates that we did the observation. So I mentioned to you, we plan to do from 1 to 100. So we did our survey for a small region of the sky from 1 to 4 gigahertz, and we completed the entire survey from 4 to 8 gigahertz. We are still, so the series, in the next series, paper number 2 and 3, we are going to extend this to higher and higher frequencies. This is only the survey result up to 8 gigahertz. And these are the different dates that we did the observation. But what's interesting is to look at table number 4. So our data is what we call baseband data. We collect the raw baseband data from the telescope, and during the offline process, we produce different kinds of resolution data product. We produce data with extremely high fine frequency resolution. Now, in the field of SETI, these kind of signals are very unique. The reason for that is that there are no natural processes to produce signal which are extremely narrowband. Like most of the astrophysical measures that you see are pretty broadband. They are actually few hundred kilohertz wide. Or in fact, there are a few kilohertz wide, but there are no astrophysical phenomena as of we know right now, which are only few hertz wide.
Right.
Only thing we see which is few hertz wide is our own technology, because we produce a lot of artificial signal and we produce this thing called carrier wave. So when we transmit, for example, to satellites, we transmit to our Wi-Fi, everything has a kind of like a carrier signal, and these carrier signals are extremely narrow.
Right.
We think that kind of a signal is very unique. And if you transmit a signal which is extremely narrow band, there is no way anybody would confuse that with an astrophysical phenomenon, because there is no physics or there is no astrophysical process that can produce it. So if ET broadcasts a signal, again, this is a similar thing like Schelling point. Like, what is the most logical kind of thing that you can think about? Because we don't know what are the ideal ways you can communicate. We try to think what's the best way by you can conserve your energy, where you don't have to kind of produce a lot of energy. I mean, you can always blow up a lot of energy out, yeah, and and that would definitely draw everybody's attention. But in terms of like conserving the total amount of energy that you need to spend in order to broadcast yourself, remember, you want to do this not for a very short amount of time, but you need to do it for hundreds of years in order for you to be detected. If you do it for only like a small amount of time, the chances that somebody might be looking towards you will be very small. So it's better to do this over many, many, many years. So what's the best way by you can conserve the energy? So if you transmit the signal with extremely narrow band that conserves your energy, there is no way that it will be kind of mischaracterized as an astrophysical. So these are the kind of signal that we look for. There are also other kinds of signals we look for, which we call the broadband signal. So similar to narrowband signal, broadband signals, if you scroll down, so we try to look for signals which are also not possible to produce in nature. I'll come to these results in a little bit later, but let me show you, since we are talking about the broadband, there is a plot. So can you, so let's keep scrolling down.
I'm sorry.
Yeah.
You want figure 5?
No, we'll talk about figure 5 later. I mean, that's kind of, yeah, we can talk about 6 a little bit later, go down. We can talk about this later. Yeah, this is what I wanted to show you.
Okay.
So in that table, what you show, what we kind of outline is that narrowband is not the only signal that you can search for. There are also other types of signal which we think can be used as beacons. These are like examples of that. People, I mean, I guess whoever is listening probably might have seen the plot which is on the extreme left. A typical fast radio burst or typical pulsar produce this kind of dispersed signal, where your signal, when they passes through this electron medium in the interstellar medium, the highest frequency reaches us first and the low frequency reaches us later due to the dispersion. So you see this kind of dispersion sweep across your band. So these are just for simulated pulses, but what we want to highlight is that, so that's an astrophysical source. But along with that, there are these 3 other artificial dispersion, which nature doesn't produce, because there are no natural processes that can produce them. So if I send a signal, which is what we call negatively dispersed or artificially dispersed, that's a way to kind of send announce yourself. Okay. So if you detect a signal like this, similar to like narrowband signal, there are no astrophysical processes which are producing them. If you detect them, that's a good sign that they are produced by artificial processes. So there is some intelligent life which must be producing them. Okay. So we went ahead and searched for them as well. Right. So we try to search for 2 different kinds of signal. Narrowband signal, which is extremely narrow in frequency, like only few hertz wide, and broadband signal, which are pretty broad across 4 gigahertz of band, but they are very much concentrated in time. So they are only like few millisecond wide. So you go to other extreme. You in one case you went to frequency extreme, the other case you went to time extreme. Okay. But you kind of change your dispersion to kind of really add artificiality to it. Yes. So that's why this added artificially help you distinguish what's real and what's not real. Cool. the other, I guess we can skip the other plots. That's just showing you what are the different number of candidates we get. We get like millions of candidates. That just kind of shows you all that. But we can just go to the results now. So if you go scroll down, so table this shows you rough number of candidates that we get. You can see there are like thousands and thousands of candidates that we typically get in any direction. So
okay. Mm-hmm.
So what I'm showing you here on the left side are these individual beams. So I mentioned to you, like for covering the region of the sky, we divided into multiple smaller beams and we named them A, B, C. So we look at a pair of beams, because as I mentioned, like when you want to discriminate signal which is coming from sky or not, you look at pairs of beams. So these are pairs of various beams where you compare the signal. And then I'm showing you that individually how many candidates you get, and how by comparing the pair F2, what is showing you F2 events is how many candidates you get from a single beam. And F3 is kind of when you compare the signals from like in multiple beams together and you see things which is only present in one beam and not in the other.
Okay.
So by this way, we can eliminate as many false positive as possible. It is still not doing a great job because you still end up having thousands of candidates, which a human has to look through, which they did. So I really want to give a credit to all this work to our second author in this paper, which is Karen Perez, who is a graduate student at Columbia University. Karen actually led a massive work of looking for these extremely narrow band signal across all of our data that we have collected. So she built the pipeline to really search for this signal and how do you compare between these different beams. It's a kind of massive task. And she also kind of looked through all these candidates visually. It was a daunting task because she had to kind of sit around and look through thousands of these plots in order to find out if there is any interesting thing out there or not.
All right.
So I do. Yeah. So Karen she's kind of led a massive work on that regard. Plus, she also made the observing plans and strategy, like how are we going to observe these individual targets. So yeah, it's and our second paper in this series actually led by Karen herself, because she is going to kind of continue this to other higher frequencies and other telescopes. So she is going to lead the project further.
Great. Yay, Karen. There's a shout
out.
Okay.
Let's go down. So let's just, I guess we can summarize the results that we get.
Okay. So we did the tables.
Yeah, I can just briefly mention, maybe I can mention about this plot. So as I said earlier, that galactic center is a region which have highest sort of amount of energetic activities. There is a magnetar you might know about, that's called the Galactic Center magnetar, 1725-2900, which is kind of pretty active. It produces these bright radio bursts all the way to, I guess, around 200 gigahertz. So the Galactic Center magnetar produces this bright dispersed radio pulses. So it kind of shows up in our data as well. So when we looked at the Galactic Center, the plot on the left, what you are seeing, you see multiple panels. The top panel is the actual detected pulse. The second panel from the top is the de-dispersed plot. So when you actually collect the data, you de-disperse it. And that's the vertical line you're seeing there. That's the de-dispersed signal. I'll skip the panel number 3, but the panel number 4, you can see the actual dispersed signal that you are seeing. So that's the real data from the Galactic Center magnetar. So by detecting it, we kind of demonstrated the quality of our data, the uniqueness of our data, that these data sets are useful to kind of look and study the Galactic Center magnetar, because nobody has done like some kind of a broadband study of the Galactic Center magnetar. Okay. So because we will be searching the Galactic Center from 1 to 100 gigahertz, which will allow you to kind of study these properties of single pulses from the Galactic Center magnetar all the way across these high frequencies, which is kind of pretty interesting and quite unique in its regard. So we wanted to highlight that in this paper, that yeah, there is an astrophysical problem that you can solve by using this data. So we wanted to kind of highlight that as well. Okay, we can come down and scroll down to other results. And on the right side is a plot of an artificial signal. So it's kind of a similar to signal, but it's an artificial signal that we injected and we detected. So as I mentioned, Yeah, so it has a negative dispersion where your signal arrives at low frequency first and it drifts in high frequency. No astrophysical sources have produced this, but this is artificially produced. Unfortunately, the bottom line is that we didn't detect it, but it allowed us to do a very sensitive survey.
Yeah. Very good. Okay.
So we can skip figure 10. This is fine. Figure 11 also we can skip. Let's go down to the main results. Yeah, I think I can discuss this. So what are we showing here? So we are showing two panels. Panel on the left is actually comparing our sensitivity across all the frequencies that we are planning to observe with respect to some of the previous searches. So SETI is not something new. SETI has been going on for like past, I would say 60 years or so. And there are a lot of surveys that people have already conducting to look for these extremely narrow band signal. So what we are showing you in these different dots or different lines are the survey sensitivity and frequency of the survey with respect to our survey. What you would easily notice is that no survey has ever done across such a large range of frequency. Most of the surveys has been done close to 1 gigahertz. The reason is quite natural because you heard about this. Again, there's the argument of sharing point. Like if you want to transmit a signal, what's the ideal frequency to send a signal? So people in the SETI community argue that it's a hydrogen frequency. It's a 1.4 gigahertz is the ideal frequency because just like the galactic center is an ideal place because everybody will be looking at it. 1.4 gigahertz is a frequency that everybody would be looking at because there is so much hydrogen in the universe. So any radio astronomer, any extraterrestrial radio astronomer, they would build a telescope to detect those frequencies. So if you send a signal at that frequency, you will easily be detected. So most of the SETI surveys you can see have been done at those frequencies. But we want to kind of relax. We want to relax that assumption. We want to kind of search other frequencies as well. So as you can see, the red line is showing you the frequency coverage of our survey. It kind of expands to all the way across, which no other survey has kind of carried out. In terms of sensitivity, we are moderately better than some surveys, but not as good. And the reason is because the galactic center itself is so bright that in order for any signal to be detected, that the signal needs to be a little bit more brighter. So if you're looking at the nearby star, the background from the nearby star is not bright, but the galactic center, if you're looking towards a star actually behind, and when your galactic center is behind that, the background itself is so bright that you need to really have a bright signal. So our sensitivity is limited in that regard. But still, we cover large part of frequency coverage. On the right, I'm showing you similar frequency coverage, but for our broadband kind of signal. So I mentioned we have two classes of signal. On the left, we are showing you sensitivity limit for narrowband signal. On the right, we are showing you sensitivity limit for a broadband signal. For various kind of pulse width. So if the pulses are pretty narrow, like 0.3 millisecond, then our sensitivity is a little less. But if the pulses are 180 millisecond, then we are a little bit more sensitive.
Very cool.
Okay, so let's go down to the, I would say this is, I guess, one of the main conclusion or the main thing that we would like to highlight. So what I'm showing you here in this plot, this is actually, part of it is taken from our earlier publication in 2017 which was led by our graduate student, Emilio Enriquez, and credit to him to kind of produce this figure. We actually just amended our extra survey on top of it. So what we are showing you here are two axes. One is the EIRP. What is EIRP? EIRP means it's the total amount of isotropic radiated power, effective isotropic radiated power. So let's say you have a civilization. If it is broadcasting signal, what is the typical power of these signals? So you can put that power in volt and you can calculate that what is the total output of a civilization. So let's say you have a powerful telescope like Arecibo, which is no longer there, unfortunately. My heart goes to all astronomers who have, including our team who was kind of using it. So if you have a telescope like Arecibo, broadcasting signal, that is something of the power of 10 to the power 13 watts. So as you can see in these log scale plot, the gray line is that region, that this is the power that is output from the Arecibo radar. Now on the y-axis, we are showing you the transmitter rate. So how many number of transmitter out there? This is kind of like a luminosity function for any astrophysical sort of sources you can draw, like number of sources versus the intensity, right? So are there more number of bright sources which are broadcasting, or are there more number of weaker sources? So we know that there are more number of weaker sources because we have not detected many brighter sources from some of the large surveys that we have done. So what the gray line is showing you is our current limit. So all the different dots you see are typical, actually giving you the limit of transmitter rate at a given power level. Because each survey will be sensitive to detect some n number of transmitter because they are looking at some part of the sky. So they are sensitive to detecting some n number of transmitter. And then they have some sensitivity of detecting the signal itself. So that's your power limitation. So you put both of them in two axes, and then you have transmitter rate, that how many number of transmitter out there, like whether you have one transmitter per 1,000 star, one transmitter per million star, right? So that's the transmitter rate we have. So 10 to the power -6 means one transmitter per million star. If you have 10 to the power 9, that is like one transmitter per like a billion star. So that's what the transmitter rate is kind of showing you that. And these are different surveys that people have done so far. What is important to notice is that before breakthrough came along, before the whole breakthrough listen was kind of came into the picture of SETI field, the limits were not really great. But as you can see, the paper Enriquez et al. In 2017, which was our first paper from breakthrough listen, it pushed the limit down. So if you can see all the points which are there, which is quite high. So earlier surveys were not able to constrain the transmitter rate at lower EIRP. Obviously, there were surveys which constrained the transmitter rate at higher power, because you can look at a large part of the sky and you can see, okay, if you look at, or you can look at an individual galaxy. So that's what the survey at the high end you are seeing. So the dots at somewhere around 10 to the power 19 volts, those are actually survey of Andromeda galaxy. So you look at the entire galaxy and you kind of see because you're looking at a billion stars. So you see that if there is a powerful transmitter of the power of 10 to the power 19 volts in a billion star, you would be detecting it, but you didn't detect it. So you put a transmitter limit there. But if you talk about transmitter rate or power for low range, most of the surveys were not very sensitive. So breakthrough kind of came and pushed that limit further. So in 2017, our limit was on that orange point, but in the price et al. In 2019, we even push it down because we survey more number of stars. And with our Galactic Center survey, it's currently showing in that star region, you can see the blue star and the orange star. So we even kind of lower or kind of made that limit even lower. So the reason was that because we were looking at the Galactic Center, and as I mentioned, Galactic Center has a large number of stars. So in fact, we roughly calculated and we found that we were actually looking at something around 60 million stars. So comparing the sensitivity of 60 million stars, we were sensitive to something to the power of 10 to the power 18 volts of power. The dotted line you see there is the total output power of what we call Kardashev type 1 civilization. So as you know, Kardashev has this scale of galactic civilization being how advanced they are. So type 1 civilization is a civilization which is able to harness all the energy of its planet coming from its parent star. So it's something of the power 10 to the power 17 volt. Obviously, we are not there yet, but you can envision other advanced societies to produce signal, which is as bright as K1 civilization. So I think the final, I'll just wrap it up. The final conclusion is that although we didn't find a signal of artificial origin towards this direction, we were able to push the limit down even further of what we already knew. So that is the main conclusion. And then I guess our survey, future survey will tell us more that is there any other artificial signal present at extremely other higher frequencies where no SETI has ever been done. So that's a unique thing because nobody has looked at this kind of signal at higher frequency above 50 gigahertz. So you may never know. Maybe there are lots of signals out there above 50 gigahertz, it's just nobody has looked at it. So we are hopeful that by extending the survey to these higher frequencies, we will be kind of detecting we will be pushing the limit in the frequency parameter space as well, which has kind of remained unexplored so far.
Yeah.
Yeah, I think that I'll wrap up with that. If you are just interested, maybe you can go down. That's just a cartoon version of a transmitter sitting at the galactic center, and maybe if it's a rotating beam, and what is the typical sort of its period that we can reject. So we did a calculation that how often that transmitter needs to kind of point towards us in order for us to detect it. So what is the probability of rejection of the rotation?
Right.
So because we observe the galactic center for a certain amount of time, so we can say that certainly no transmitter we're actually rotating with a period of something around seven hours or so, or 6 hours or so with 100% probability. But if you go to higher sort of period, if it's rotating slowly, like if it's pointing towards us, maybe 1 in 100 hours, then our chance detection is maybe just 10%.
Yep. Cool.
Yeah, and these are some examples of the galactic center magnetar we detected. We wanted to demonstrate the wide varieties of different things that we saw. Again, kind of pointing out that there are whole new astrophysical phenomena that one is able to discover by using the same data set. So this data set, as I mentioned, will be open to public. So it's going to be, anybody in the community will be able to download all the data, look for pulsars, study galactic center magnetar. They'll be able to do a whole lot.
What's the total size of the data set?
Oh, it's kind of hard to give the total number because it depends on what is the resolution that you want to keep the data in. Typically for 5 or 6 hour observation, when we collect the baseband data, it's 400 terabytes. So like 4 hours or 6 hours of data is around 400 terabytes or so.
Okay.
We reduce it down to few terabytes. So you can think about like a few tens of terabytes for a few hours. So 600 hours is going to be a few hundreds of terabytes.
So first of all, Vishal, thank you very much for walking us through that really paper number 1. And so the reason I was asking the question was sort of as a lead on to, where do we go from here, given what you've published? And you mentioned a few things. And so I was wondering on the size of these data sets, and you said people could download it. I wonder if there's, a public citizen science component to this. So people, much like the traditional SETI, people will download just a chunk of it and do the analysis on that chunk.
Yeah.
Is there?
Yeah. So all that there's a link in our paper where you can go. There's an open data portal link which people can go to and download the data that we have presented in our paper. Okay. And it's open to community. And if you go to our Break to Listen website, we have given a detailed instruction about how one can search for type of signal that we search for. And anybody are open to develop their own algorithm. All of our data, this is one of the cornerstone of Break to Listen. Like all the data we collect are going to be public. We don't really have a proprietary period that we want to retain it. We want to make it public as it's physically possible for us to do so. So all that is public. You're open to kind of go to our open data portal and download any data that we have put there. This data set we are going to collect is also going already available, but future data will also going to be available on the same open data portal.
That's awesome. So we'll put a link to that data site in the description below the video. So that'll be really cool. So you mentioned papers 2 and 3 coming from the survey. So do you imagine there'll be 3, 4, and 5? And are there other telescopes that could help with this search? Are there additional theoretical calculations that could be done in the interim? And just, sort of where do we go over the next 5 years?
Yeah, great question. Thank you for asking. Definitely. So paper number 2, we are going to expand with the same telescope to higher frequency. So we have already collected data earlier this year up to 10 gigahertz. So we surveyed this galactic center from 8 to 10 gigahertz, which was not included in this paper because that data was very recently collected. And that was going to be part of the second paper.
That's Karen's.
Along with that, along with that, very recently we have started collaborating with this telescope in Italy called Sardinia radio telescope.
Okay.
Sardinia radio telescope is 64 meter in diameter. So it's not as big as the Green Bank telescope. Green Bank telescope is 100 meter in diameter, but it's still sensitive.
Right.
But the best advantage of Sardinia radio telescope is that it can also go to higher frequencies. And they are recently upgrading their receivers to go to other higher frequency all the way to 100 gigahertz.
Ooh, okay.
So we already have instrument deployed. We have Breakthrough Listen is collaborating with the Sardinia radio telescope. And we have already deployed instrument, and we are already conducting a survey. We have actually completed a small part of higher frequency, which didn't cover with the GBT, something around 20 gigahertz or so. So 20 to 26 gigahertz. We have already started doing it with Sardinia radio telescope. So in paper number 2, we'll also be including data from Sardinia as well.
Nice. Very cool. I'm looking forward to the next couple of years when we see some of these papers rolling off. It's going to be really great. Put some new limits or with a little Lexum detection. That would be cool too.
that would be excellent. Yeah. Then I can park in front of my building because then I can get a Nobel Prize. Well, I don't know whether you know this. Like in the UC Berkeley, it's very hard to find parking. You don't. I mean, we have to park outside. You have to park outside the campus. Only Nobel laureates get to park inside the campus.
Oh, well, I wish you a permanent parking pass coming into the future there, Vishal. Heck with aliens, I just want my parking pass.
That's a good motivation, I guess.
Absolutely. That's fantastic. All right, that'll do. Vishal, thank you again very much. And everyone, I hope you enjoyed it, and I hope it made your astronomy day just a little bit better. And we'll see you on the next one. Thank you. Bye-bye.